let's solve some problems. So the first problem we're going to solve, I'm going to solve this problem in Ruby. It's called Wonky Coins. So let's see what it's all about. Castlevanian money is a strange thing. They have a coin for every denomination, including 0. A wonky change machine in Castlevania takes any coin of value n and returns 3 new coins, valued at n over 2, so n divided by 2, n divided by 3, and n divided by 4, rounding down. This is going to be important to take note of, right? Especially what language we're going to be using it. And for me, like I said, it's going to be Ruby. Write a method called Wonky Coins that returns the number of coins you are left with if you take all the non-zero coins, right, non-zero, and keep feeding them back into the machine until you're only left with only 0 valued coins. Difficulty is 3 out of 5. All right, so let's see some examples. So Wonky Coins of 1 will be 3, all right. Wonky Coins of 5 will be 11. Wonky Coins of 6 will be 15. And Wonky Coins of 0 will be 1. Okay, so that makes sense because we're going to once the coin is equal to 0, that's when we're going to start counting. So we're going to see the total of zeros, which is this, right? So how many times that shows up. All right, I'm going to assume that I'm always going to have some sort of number, right? Some sort of whole number. I'm not going to get any strings like that here. Any sort of a weird like an array of numbers. It's going to be a single integer. Whole number is given to me. All right. So let's think about. Got a little stuff we got to erase here. Oh yeah. Let's think about kind of the logic behind this right now. Rounding down. The thing with Ruby is that if a number is an integer divided by another one, it's going to automatically round down for you. Okay. So for example, 5 divided by 2 is just going to be 2. It's not going to be 2.5 or 3. Okay. So let's do this. Wonky coins. All right. So Wonky coins of 3. So already have this as an example, right? So Wonky coins of no, we don't. We have Wonky coins of 1. Let's do that. Let's see how that makes sense. Let's see why Wonky coins of 1 is equal to 3. Okay. So Wonky coins of 1, right? I'm putting WC for Wonky Coins. It's just easier for write. This is a new little drawer I'm using. Not new. This is the first one I've probably ever done for videos. It's actually the first video I've ever made. So bear with me here. So Wonky Coins of 1. How does this work? So is Wonky Coins of 1 over 2, right? And Wonky Coins of 1 over 3, and Wonky Coins of 1 over 4. Right, so 1 over 2, 1 over 3, and then 1 over 4. Okay, so 1 divided by 2 in Ruby is going to be equal to 0. Okay, and then 1 divided by 3 in Ruby is also going to be equal to 0. And then 1 divided by 4 is also going to be equal to 0. Okay, there's no remainders, there's no decimal point. None of these are floats, right? So you can only if you want to make a remainder, you just have to make one of these numbers a float. So you can put a dot and then put a 0 there. You just put dot to f dot, and Ruby would be dot to f, I believe, underscore to f to make it to a float, right? Should probably double check that. So, anyways, so they're gonna count these up. So 0 plus 0 plus 0, right? For us, is actually 1 plus 1 plus 1, and the answer for us is going to be 3. Because once the coin is equal to 0, that means it's actually equal to 1. For all intents and purposes, it's equal to 1 for us, right? Because we're counting it. We're counting the zeros, and that equals to 3. Okay. And as you see over here, Wonky Coins of 1 is equal to 3. So that makes sense. As you can notice, things start getting pretty big pretty quick. So the main logic of this is that you guys are going to keep on feeding the non-zero numbers back in, right? The non-zero numbers back in. But once it is equal to 0, you're going to return something, right? And you're going to use something to solve this called recursion. And the first step to recursion is to figuring out the base case, right? The base case for this is if n, whereas if the number coming into the Wonky Coins is equal to 0, then what am I going to return? We already talked about how 0 for us is essentially equal to 1, right? So then I'm going to return, I'll put R as return. I'll return 1. Okay? And that if, right, but now if it's not equal to 1, what am I going to do? Well, I'm going to take all the non-zero numbers, right? So then, essentially, I'll take Wonky Coins. So if n coming in, the n coming in, is not equal to 0, that means it's a non-zero number, then I'm going to take Wonky Coins, let me leave this right here. Then I'll take Wonky Coins of whatever of n over 2, and then n over 3, right? And then n over 4, okay? And I'll send that back into this machine until it gets all the way down to that, and this gets down to 0, and then this gets down to 0, and then this goes down to 0, and then we'll turn all this again. Okay, so once I write this out, it'll kind of make a little bit more sense. So here we go, here's the base case. So if n is equal to 0, right, what am I going to do? I'm going to return 1. Cool, so that's the first thing. Next is going to be the recursive step. So here, I'm going to take Wonky Coins. Right. Oopsie daisy, did not mean to do that. I'm going to take Wonky Coins here. Copy, boom, 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 right there. And then I'm going to return the result of Wonky Coins of n over 2, and then n, copy in n over 3, and then copying in Wonky Coins of n over 4, right? That is what I'm going to return. Now, think about this. So, this is not correct syntactically. You can't just put combos like this in between these things. It's not really going to make much sense, right? You have to put some sort of structure here. All right. Yeah, you put some sort of structure, like using an array. Okay, but I'm just writing out almost exactly what I told you guys to do here. But the thing is, we want to return the total number, right, of zeros. Okay, so what I want to do here, actually, if I think about it, let's go back to our example of if Wonky Coins of 1, right? So this means that these n's right here are actually equal to 1. Boom, 1, 1. Right, and like I said, once is equal to, so is equal to 1, right? And 1 by 2, this is actually equal to 0, right? And this is equal to 0, and this is equal to 0. Now you want to add these all together, right? Technically, you want to add these all together, right? Remember, now 0 for us is equal to 1, given this step right here, okay? So that would give us, boom, 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 equals to 3. I'm just going to follow that same logic here. I'm going to go Wonky Coins plus that, Wonky Coins plus that, okay? So I'm going to keep on staying that back in the machine. It's going to make a big, huge recursion tree, and it's going to add up all the zeros at the bottom, right? So let's go on, run it and see if it works. See, it says true, 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 true. There it is, and there you go. In the next video I'm going to show how to make this algorithm more efficient using memorization.